This video is about spectroscopy. Remember the electromagnetic spectrum? The energy of light is dependent upon its wavelength and its frequency. E equals h nu, C equals lambda nu. All those lovely equations. This is here a picture of the electromagnetic spectrum. Shorter wavelengths over here, gamma rays. Shorter wavelengths, higher frequency, higher energy. The wavelength gets longer and longer through X-rays, ultraviolet, visible, infrared, microwave, radio. We spent a good amount of time in your first year chemistry class talking about light. And you may have wondered at the time why. It's because light interacts with atoms, and we can learn a lot about atoms that way. We've already done Beer's law. Beer's law is an application of UV vis spectroscopy, ultraviolet visible spectrometry. When light in the region of ultraviolet or visible, and of course the stuff we were doing was visible light, when that light hits a molecule or an atom, the electrons change orbitals. This particular picture shows a theory called molecular orbital theory, but it's similar to what you've already heard. Electrons just go up to higher energy levels. That's absorbance. And then when they fall back down, that's emission. There's such a thing as absorbance spectroscopy. There's such a thing as emission spectroscopy. Here, for example, is a UV vis spectrum. It's different than the ones we did because the ones we did were at one particular wavelength, whereas this one is a graph which is a range of wavelengths, and again, absorbance here on the y-axis. So if we did this with the blue dye, we would have a wavelength max at 655, which is where we actually did the experiment. So when on our colorimeters, when we do it, we're looking at the absorbance at one wavelength. But they also have spectrophotometers that do a graph of wavelength, or absorbance versus wavelength on the x-axis. But there are actually other kinds of spectroscopy. One very important kind of spectroscopy is infrared spectroscopy. This is the kind of spectrum you get from infrared. Now, once again, this is a different area of the electromagnetic spectrum. Let's go back to the electromagnetic spectrum. Infrared's over here. It's lower in energy than the ultraviolet and the visible. So when we are talking about infrared, we are not actually talking about electrons moving. This was actually a misinterpretation that I had in my mind for a long time. But it isn't electrons that are moving in infrared spectra. It's actually the molecule itself. In this picture shows you some of the movements of molecules: symmetric stretch, asymmetric stretch, bending, vibrating of various kinds. That's the kind of thing that infrared light, that level of energy, does to molecules. It causes it to stretch or vibrate or bend. If you're looking at an IR spectrum, you might see something like this. This is actually kind of upside down, if you will. If you think about the UV vis, we had a peak that went up. These peaks go down. This is your peak. It starts up here, goes down, and up, back up again. This big, huge thing here is a CH vibration. This one here is a C double bond O stretch. All right. So different things have different stretches and bends and vibrating, but they come at the same place. So a big, giant, thin thing at 1700 always means there's a C double bond O in there. There's something over here That could be an OH, for example. Here's one. Vanillin. So you'll see it does have a C double bond O right there. And there's my C double bond O peak at 1700. This one here, if I remember correctly from back in my day, that's the OH. And then this part over here, this is called the fingerprint region. It's different for different molecules. So there actually used to be big books. Now there are databases online where you do the IR for a particular molecule that you're interested in, and you can match it up and say, ha, see, this is I really made what I think I made because the IR spectrum matches what I see in a previous spectrum from something I know to be this stuff. Okay? So my point essentially is that the different wavelengths of light interacting with molecules cause different things, and we can use that to tell us about molecules. IR and UV vis are both ways to do that. There are others. There's NMR. That's not light, though. That's magnetism. But that's another really common. They take the sample, I put it in the NMR, and I see the spectrum, and I match it with known spectra. There's also mass spectrometry, which we talked about earlier. That's the one where it shows you the different isotopes, or it shows you the pattern when it breaks apart. So these are just various ways that scientists use to learn about things that are too small to see.